Today is January 5th, 2023. This is my 204th episode for C++ 17 2023 SQL OpenCL TBB Balkan. This is my 34th episode for vector calculus. I will rename Green's Theorems 1. Double integrals in polar form. I first encountered or learned Green's theorems back in 1987. It was around July or August when I first taught myself vector calculus using Thomas's calculus, either 4th or 5th edition. After 36 years later, now I implement it in C++ code. In this episode, I will discuss Green's theorem, also double integrals in polar form. I implemented numerical integration from episode 154 through episode 159. Numerical integration 6, multiple integrals 3, double integrals completed. If you haven't watched my previous videos about numerical integration from this playlist, starting with episode 154, see the pop-up window, Numerical Integration 1, Adaptive Simpson's Quadrature. From episode 154, Numerical Integration 1, through episode 159, Numerical Integration 6, Double Integrals completed. I assume you have watched my previous videos about numerical integrations. Otherwise, you may not understand how to implement numerical integrations for double integrals or triple integrals. From Thomas's Calculus 13th edition, chapter 15.4, Double Integrals in Polar Form, page 901. From Thomas's Calculus 13th edition, at page 901. Here you can find double integrals on polar form. We will be using this formula in my current episode. There are two Green's theorems. One is circulation curl or tangential form. The other is Flux-Divergence or normal form. We will solve example 3 in page 987 from Thomas's Calculus at page 987. We will solve example 3. Verify both forms of Green's theorem for the vector field. This vector field and the region are bounded by the unit circle. This circle. We will solve this problem. Without further ado, let's get started. Open up Visual Studio Code. From CPP 17 2023 parallel, select empty space, click this button, 204 Green Theorems. Click this button, green.cpp, hit enter, Ctrl V. I will close this document. I would copy and paste these links for future Thomas Kim who would watch this video. If you scroll down, you can find C++ library extensions. To follow my current session, you need updated C++ library. After filming video, you may Ctrl-click this link to download updated library. Ctrl-End, Ctrl-Home. I will fold it up. Here, include CPG, SCD, extensions. include CPG, CPG, calculus, namespace, CNA, CPG, numerical analysis, namespace, CPT, CPG, types. I will arrange side by side like this. We are going to solve this example. Here, void test, green circulation curve, into main, copy, test green circulation curve, SCD, cout, green circulation and curve, GPG and L. We need using namespace, GPG, operators and constants. Using namespace, GPG, numerical analysis. Comments. We will define this vector here. Or F. CPT make tuple. This is function. Or square bracket or x or y or z. Return x minus y. Semicolon. I will remove line break. Copy, paste. Then x. Here. Remove trailing comma. I will remove this space. Let's move on. Or R, CNA, create, BCTR, 3D. This is function. We define this curve. Here, t is greater than or equal to 0, less than or equal to 2 pi. Here, we define x like this. Square bracket or t, return SCD, cosine t, comma, copy, paste, sine t. Let's try to build to double check the syntax. Open up command prompt. dir cd 204 green theorems. clang std c++20 green .cpp ltbb 12 or c.exe, hit enter. Okay, it built. Now auto circulation R line integral TDS. We pass F. SCD cout circulation we pass 0.0 then 2 pi. Because t is greater than 0, less than 2 pi. In this figure, our curve is parameterized with t. T is angle from 0 to pi. So from 0 to pi. With this, we can build again. I missed XY plane. Please understand, we implemented in our previous episode 203, Control N. We implemented this function in our previous episode. We build again. CLS, we build again. Okay, it built. C. This is correct value. This is 2 pi. If we double check, this is 2 pi. This is circulation. Now, this part. In this book, Thomas's calculus, vector f is represented M, I, N, J, P, K. But I hate this notation. Instead, I use F, Xi, Fy, J, Fz, K notation. With this notation, I don't need to remember this silly formula. I don't. I can do it intuitively. Although density, we capture f. This function f is defined here. We need auto x, auto y, semicolon. Now, auto fx, fy, we extract function fx and function fy from vector f. Now, auto d fy over dx. This represents this part, round n over round x. CNA partial derivative. We differentiate with respect to x. So dx1. We pass n. N means fy. So fy, we pass x, y from parameter. But this function takes 3 arguments. So we pass dummy value for z. Copy, paste. Now this is fx over dy. We are computing this part. We are differentiating with respect to y, because dy, also dy, then it should be fx. The remainder is the same. You can say fx is for m, fy is for n. With this, return. This is forward direction. This is reverse direction. So dfy over dx minus dfx over dy. Here, forward rotation. This is backward rotation. You may not understand what I mean forward rotation or backward rotation. I will discuss such things in future sessions. We defined density. This density is called circulation density. Now we have to convert it into polar form, or density polar. We capture density or r or theta. We are converting to polar form, or x, SED, cosine theta. I missed r, or y, r times SED sine theta, we converted to polar coordinates. We converted from polar coordinates to rectangular coordinates in this case because we are going to call density like this by passing x and y. But this is not good enough. We need multiply with r. I will discuss this part shortly. Don't forget semicolon. Because we defined density function on rectangular coordinates. If you scroll up, we defined f on rectangular coordinates. We need to convert from polar coordinates to rectangular coordinates. But this is density function on polar form. Now, here, oracle CNA integral. We pass density on polar coordinates. We have to pass CPT, make tuple. This is a function. The radius, okay, radius runs from 0 to 1 because this is unit circle. This is for radius from 0, 1.0. This is bound of the radius on polar coordinates. Then CPT make tuple 0.02 times pi bound of the angle theta. Angle theta runs from 0 to 2 pi. Now, here we have to specify the meaning of these bounds. We defined angle theta here. So, dt, then we defined bound of the radius, or r. So, dr, semicolon. But I haven't defined this operator yet. Control Home. I will fold it up. Right click. Go to Definition. In this file, right click Vector. Go to Definition. In this file, right click. Go to Definition. If you scroll down, you can find comments. Now, in this section, you can find dx, dy, dx. These are defined like this. Now, you can copy, scroll down. I will make demarcation and paste. Now, this is dr, dt. This is dt, dr. If you want to understand what these things means, then you have to watch my previous videos about multiple integrals. I will make it bigger. From this file, here in this section, I explained what these things are in these videos. So, if you haven't watched my previous videos from episode 154, 159, you may not understand what these are. I cannot explain because I already explained through these videos. Now we defined dr, dt, dt, dr, the values are defined like this. With this control end, this should build std, cout, col, I will put comma here, col, cpg, and L. Don't skip or miss my videos. If you skip or miss my videos, you cannot understand my current and future sessions. With this, we build. Wow, we have error message. I made a typo here. 139. 39. I removed oro x, oro y. Rebuild CLSC. Wow! Circulation curve matches exactly. These are very accurate computation because we used polar coordinates. If I implemented this part on rectangular coordinates, the result would not be very accurate. Now scroll up from here, copy up to this point, paste. Scroll up, I will rename test green Flux-Divergence. Copy this function name, control N, paste it here. Now scroll up, green flux and divergence. The function is the same. R is the same. Now this is not circulation. This is flux. We implemented NDS in our previous episode. So if you missed my previous episode, please watch it. We implemented this function in our previous episode. It is now flux. Scroll down. This part is now should be changed. This is divergence density. This is now should be fixed. dfx dx fx. This should be fixed. fy dy fy. Delete this. dfx dx plus dfy over dy. Now this part is the same. This is divergence. Copy, paste. With this, we build again. CLSC. Wow! Green flux and divergence. Flux 3.14159. This is phi. Divergence 3.14159. Divergence, flux and divergence matches. We perfectly solved this problem. In case of divergence, the answer is phi, flux phi. We solved example 3 perfectly. Now, let me explain this part. Please understand, we implemented density function using partial derivative, more specifically divergence density. In this case, we used rectangular coordinates, but we do integration using polar coordinates on the plane. Density polar. From polar coordinates, we converted to rectangular coordinates because density this function we do derivative on rectangular coordinates. What I am saying is that we intermixed rectangular coordinates and polar coordinates. We used double integral. In this case, when we compute flux, internally it uses derivatives with single variable. This is plural derivatives because internally it differentiates twice. Once to evaluate unit tangent vector, the other to evaluate principal normal vector. But in this case, we used partial derivative. This problem is very much advanced. Now I will explain this R. Here, chapter 15.4, double integrals in polar form. If you scroll down, in this formula, dr d theta, we need to multiply r to integrand. This r represents this r.